So which slide? There we go. Okay, so the first objective is not only is it rehashed, but it's also there's a lot of material in there that's out of date, and if you want up-to-date information, look at the CSA B52 code. I highly encourage, if you don't have it already, get your hands on it. You can use it in the ABS exam, and of course you can use it in my final. You can use it everywhere, right? And read it over and be familiar with it, because a lot of that stuff is in the B52. Now try and get a current B52, because things have changed. And in your third class, there's a bunch of stuff quoted from the B52 that has changed. So for example, safety grouping for various refrigerants has changed. So you're going to either need to pull open your fourth class or look at the B52 code to see what the safety classes of refrigerants are, because what's in the third class is no longer applicable, no longer relevant. So objective 1 also says explain the required properties of a refrigerant and describe the 6 group classifications. Well, these here, those are the groups that I'm talking about that are in the CSA, and these are the safety groupings. And so what we have is an A group, and we've got a B group of refrigerants, and what we have is increasing toxicity. So as the letter goes along, they become more toxic. And so this is one of the properties that we're concerned about with refrigerants. And then we've got 1, 2, and 3. So we've got A1, A2, and A3, B1, B2, and B3 refrigerants. And it's this middle category here that's been updated. So there's a low flame propagation and there's a high flame propagation variance, right? That should be B1 there. So the numbers refer to flammability. Now, you don't have to memorize that, but you really should have the B52 code, and you should really put a little tab in it so that you can find that table. So if you're asked on an ABS exam, what's the difference between refrigerant R290 and refrigerant R717, if it says, well, this one's more flammable or this one's more toxic or whatever, you can easily look it up on that chart. So this is something that you really should know. Then there's other things that we're concerned about with the refrigerants. So for example, miscibility. And miscibility refers to when one liquid is soluble in another. So it's basically the solubility of two liquids. Well, we have a refrigerant in its liquid state, and we've got some lube oil in the crankcase of our compressor. And so then we have to think a little bit, well, does the refrigerant sort of float on top of the oil, or does it sink below the oil, or does it mix in with the oil? And we find, certain refrigerants are miscible with certain types of lube oils, and others are not. And some are compatible with some types of lube oils, and some are not. And so, miscibility is an important feature of a refrigerant when we're considering a particular lube oil for the compressor. Other things, some of the properties are, so we mentioned toxicity and flammability is the two that give us our safety grouping categorization according to CSA. But other properties include things like, operating pressures, net refrigerating effect at standard conditions. And so this is the type of stuff that helps us to determine the operating characteristics of the plant. If we know what the refrigerant is, we know how much refrigerant we need to circulate per unit time to achieve a particular cooling effect. So these are some of the thermodynamic properties. So we've looked at some physical properties, some chemical properties. So, and then some of the other properties that we need to think about are ones that have really come to the foreground over the last, let's say, 20 years, are these two terms, ODS and GWP. And do you folks know what those TLAs mean? By the way, those are TLAs. Maybe you don't know what a TLA is. A TLA is a three-letter acronym. Okay, so these are three-letter acronyms. And so what is ODS? What is an ODS? Anybody? Or GWP? Just jump right in. Okay, an ODS is an ozone-depleting substance. So we need to know, for example, what effect a particular refrigerant has on the ozone layer. And GWP stands for global warming potential. And so we want to know for a particular refrigerant what its particular global warming potential is. Okay, so just you should be able to discuss various refrigerants, keeping in mind all of these various terms. So let's take a look at some of the things that are in the third class that need updating. First of all, this is what I was saying about the refrigerant group classes. They're properly called safety classifications or safety groupings. And these safety groups actually come from ASHRAE. I think it's ASHRAE Standard 37, I think is what it is. But ASHRAE basically is the American Society for Heating, Refrigeration, Air Conditioning Engineers. And you know, they work with CSA, and CSA basically adopts some of their stuff, including their safety group classifications. So in the third class, it's out of date. Again, look at the fourth class, edition 3, if you still got your book. If not, the latest CSA B52 has the updated refrigerant safety classes. Now, as for R12, the third class goes into a fair amount of information about R12. I got to tell you, I'm not going to quiz you at all on R12 because this stuff is phased out. It's done. Now, that doesn't mean that ABSA won't ask you a question about R12. Maybe ABSA will ask you this. R12 was phased out because of. And what would be the answer? Anybody know why R12 was phased out? Okay, let's go into R22. It was phased out in 2020. Okay, now at the time the third class was written, it was facing a phase out, but finally that came about in 2020. So a year ago they phased out R22, which means that all new production of R22 has stopped, number one. Number two, they can no longer trade R22. So for example, you can't import or export R22. What you can do is purchase reclaimed, recycled R22 that, you know, maybe they pulled out of an R22 chiller or something like that. So you can purchase reclaimed stuff only, but if you can imagine, that means that, you know, the availability is probably far less than demand. Like the demand is really outstripping the availability of R22 right now. So I would imagine if you want to buy reclaimed R22, we're looking at a lot of mucho dinero there, lots of money. So same question, why was R22 phased out? Give you a hint. It's a TLA.
I think it has to do with the ozone, the the global warming issue.
Well, it's the first one you were saying, OSS, is the ODS. They're ozone depleting substances. R12 is worse than R22. And basically, they are chlorinated uh, methane or ethane, right? So we got basically a couple of um, CFC groups, which are called chlorinated fluorocarbons. And basically, they take a methane group or an ethane group and they add chlorine or fluorine or hydrogen to some of those. Remember, carbon's got four bonding points, right? And so what they do is they substitute the hydrogens for chlorine or fluorine, and the chlorine is the baddie because it's going up and it's knocking out the ozone layer, purportedly. So R12 has more chlorine than R22, so they got rid of R12 first, and then R22 survived until last year. Okay, so then now notice that we've got all these R numbers, and one of the things that we might think is, well, first of all, where the heck did the R numbers come from? They come from ASHRAE. And then we think, oh, well, it must be a safe refrigerant. It must be good. It must be, safe to use as a refrigerant. No, ASHRAE is not concerned about the safety of these refrigerants. ASHRAE is concerned about, has a manufacturer accurately defined this particular material that it proposes for use as a refrigerant. So it would be things like, okay, well, is it flammable? If it is, how flammable is it? Is it toxic? Is it? Well, then how toxic is it? In what concentrations? Is it an asphyxiant? Is that the only danger? Is it explosive? Under what conditions? And all this kind of stuff. What's the chemical formula? What's the chemical composition? And then once the manufacturer has, provided the information that really kind of defines what that particular refrigerant is, then ASHRAE gives it an R number. And so some of the ASHRAE refrigerants are highly toxic. You get a little whiff of it and it knocks you dead. I do think that hydrogen sulfide or sulfur dioxide, one or the other, are actually refrigerants that are given R numbers. So you can see that there's some nasty things with R numbers. We've got something like R290. R290 is propane, and highly flammable, right? And then we got other ones that are immediately dangerous to life and health for different reasons. So anyway, that's what ASHRAE does. It doesn't mean that they're safe to use. What it means is that ASHRAE can give you the information about these, and they'll put them into safety groups and safety classifications so that we can apply rules so that they are applied in a safe manner. So I think that's about it for objective 1, chemical, physical, thermodynamic, economic properties. You should know that kind of stuff. And by the way, we should also know that refrigerants have trade names, they've got common names, they've got chemical names, chemical formulas, and ASHRAE designations. So let's say, for example, we've got propane as a refrigerant. Its ASHRAE designation is R290. It's got a common name, and the common name is propane. And it's got a chemical formula, which is C2H, no, pardon me, that's methane, C3H8. Okay, so that's propane. And so what have I got? I've got sort of the trade name, ASHRAE name, chemical name, and chemical formula. And so you should know that ammonia is the common name. It's NH3 is its chemical formula, and its ASHRAE designation is R717. That type of stuff. Okay. And what you're going to find is I usually use the ASHRAE designations when I'm going over this stuff. Now, this one here is the ammonia compression refrigeration cycle. And so what we're going to do is look at the refrigeration cycle that you know already, but like I said before, I'm going to just use this as a moment to refresh you a little bit. So this is a chart for R217, and in fact, it is a pressure enthalpy diagram. And so you know about pressure enthalpy diagrams, you've used them, you use them for steam, and you know in your academic supplement, there's, I think, 3 different charts for 3 different refrigerants. So every refrigerant has its own chart because it has its own specific thermodynamic properties. And so we've got on the pressure side, we've got a high pressure over here, and I'm going to say that's let's say 1190 kPa. That's this pressure, okay? And then we got a pressure down here, and let's say that that's, oh, I don't know, 220 kPa. I'm just ballparking this. These, by the way, are absolute pressures, just like you would see on the tables. And notice that for each one of those particular pressures, there's a corresponding temperature. So there are lines of constant temperature. And so, for example, this one over here is minus 30 degrees Celsius. Okay, and so then these lines of constant temperature go something like this, kind of straight up. And here they're going to go straight across. Because at constant pressure, we've got a constant temperature. And then they kind of dipsy doodle down. Okay, so those are the lines of constant temperature. And then what we have here, this line is the line of saturated liquid. And all of the points on this line we can find in the refrigerant tables for R707, H sub F, okay, the enthalpy of saturated fluid. And then we got a whole bunch of other lines here that go across, and those are lines of constant quality. So here it says X is equal to 0.1, and you know we often use the symbol small letter q, and it's dryness fraction, okay? So this one, 0.1, or in other words, is equal to 10% dry and saturated. And here we got 20%, and here we got 30%, on and on and on. You get the idea. And then, so we've got these lines of constant quality. So they connect points on the graph that show the same quality. And here we have got a line of saturated gas. And if we're looking for that information on our tables, we look at H sub G. And so then we find that, you know, say from this point on the line to that point corresponding at a constant pressure, we find that there's a certain amount of energy absorbed in the transformation of something from its saturated liquid state to its saturated gaseous state. And so in between the two lines, we've got HFG, right? The latent heat of evaporation. That's in between HF and HG. Now, other things on this chart, we've got the state of the refrigerant on this side of the line is subcooled liquid. And that's going to be important for us because we're going to keep looking at subcooling and seeing how it's important and why we want, in fact, to subcool our liquid. Now, subcooling isn't a great thing when we are dealing with steam plants, right? We don't want to subcool the condensate in our steam plant because that's just extra heat we got to add to the condensate to boil it again, right? So we don't want to subcool the condensate in a steam plant, but in a refrigeration plant, it's a good thing. And we'll take a look at very shortly why subcooling is good for a refrigeration plant. So down here, we've got subcooled liquid. Anywhere in between those two lines, we've got two-phase mixture. And by two-phase mixture, what we have is both liquid and gas coexisting, just like with steam. And then when we get above the saturated gas line, everything here is now superheated. And I know, we tend to think of superheated as being, oh, really, really, really hot. Well, we can have superheated vapor in a refrigeration system that's 0 degrees Celsius. We can also have superheated vapor that's 140 degrees Celsius. So now we've got some other lines here that I want to point out. We've got here lines of constant, well, these are isentrops, right? In other words, lines of constant entropy. And this is a very useful thing for us, very important for us, because if we have got isentropic compression, first of all, we're compressing gas. We're not compressing liquid. We're not even compressing saturated gas. We are compressing superheated gas. And if we're compressing that gas, compression process comes pretty close to being adiabatic. We could do calculations like you've done with steam plants and isentropic efficiencies and things like that. And so, we could factor in isentropic efficiencies, but for the sake of the third class, definitely what we're going to do is just assume that compression is adiabatic. And adiabatic, what is it? It's isentropic, constant entropy. So these are very, very useful lines if we're trying to trace the compression process, because it will follow lines of constant entropy. All right, so any questions so far? Raise your hands if you're kind of following me. Okay, good. Good enough. All right, enough with that already. Okay, so we got two pressures here. We got one up here, 1190, and we got one down here, 220, which means that this one here is our high side pressure. And that's the terminology we use. You need to know that, high side. And you need to know here, we've got low side pressure, and some of the system components are on the high side, some of the components are on the low side. And so one of the things you need to know is, what do you find where? Now, notice that for every saturation pressure, in this case 1190, there is a corresponding temperature. So, for example, this is the line of constant temperature, and this one here is 30 degrees Celsius. That's plus 30. And that line of constant temperature goes here, and it actually goes right across and comes out over here. You can see it again, and then it shoots down to here. Okay, so there's plus 30 degrees Celsius on that line of constant temperature. So it's kind of a zigzaggy line. So at 1190, the saturation temperature is 30 degrees Celsius. Ish. Okay, I mean, if I want to be really accurate, I look at the tables, but I'm just eyeballing this right now. And as for the low side, well, I've got the line of constant temperature of 10, and I got another line of constant temperature here. Actually, that's minus 10, and then there's minus 20 over here. And so it looks like it's sort of right in the middle there. So I'm going to say that that's minus 15 degrees Celsius, and that minus 15 line goes across, all the way across, and comes out over here and goes down here to minus 15. Now the reason when I drew this chart, I wanted you to see plus 30 and minus 15, because those are standard conditions. Is one of the things you got to know. Standard conditions that color one here. Standard conditions for a refrigeration plant. Now, that doesn't mean that all refrigeration plants operate under those conditions. Very few do. But for comparison's sake, when we want to compare one refrigeration plant to another in terms of its net refrigerating effect, in terms of its coefficient of performance and things like that, we need to pretend that all of these plants are operating under the same conditions. And so then we ascribe these standard conditions as being plus 30 condenser and minus 15 for the evaporator. Now, if we then say that all of these plants are operating under standard conditions, then we can compare them, apples to apples. Started out with boilers. We got all kinds of different operating pressures and different superheat temperatures and different feed water temperatures and blah, blah, blah. But yet we somehow, using the equivalent evaporation rule, we say, well, this boiler is so many boiler horsepower, and the other one there's so many boiler horsepower, and then we can compare the two. Or we can do things like equivalent evaporation and blah, blah, blah. So the equivalent kind of standardization that's done with a refrigeration plant is to use these two temperatures for the high side and the low side. So we got a high side temperature of 30 degrees Celsius, which means that my condensing medium, by the way, of course, this must be then the condenser. Because what's going on is we are taking a certain amount of heat at this point, and we are rejecting that heat, turning it from superheated vapor. So we lose some heat in the condenser there. So we start with superheated vapor that enters the condenser. We take it to the point where it's saturated vapor, and then we continue to reject heat until it becomes saturated liquid, and we might even cool it off a little bit more. Notice at this point here, we are no longer saturated. We are now subcooled at that point. So our condensing temperature is 30. It looks like here we're at about plus 25. Okay, so in other words, this condensing process isn't just restoring it to its saturated liquid condition, it's actually cooling it off a little bit further. And if we are going to get subcooled liquid at plus 25, that means our condensing medium, or condenser water, or the outside air that's blowing through the condenser, must be, let's say, 20 degrees Celsius max. It's got to be colder than that. So just for argument's sake here, I'm going to say that the condensing medium is 20 degrees Celsius. And that's the only way we can achieve a plus 25 temperature. Or it would have to be less than that in order to get us the subcooling effect. Now, as for the evaporation, this is our evaporator down here. And we've got a certain amount of liquid that enters the evaporator, and we know that a certain amount of that liquid is going to flash, just like when you blow off the water column on the boilers in the Synovus building. You open up the drain on the low water cutoff, and the water that's saturated in the boiler drum drops in pressure, and a certain amount of that, it has more heat in it as high pressure saturated liquid than it can have as low pressure saturated liquid. Okay? So, in other words, we're going to see flashing into steam. Well, here we see flashing of refrigerant vapor. So let's take a look at the cycle now. I'm going to clear the writing off of the screen. And I don't think that there's anything that I have mentioned so far that should be new to you. I think this is all covered in lab or in your thermodynamics classes last year or this year. and also in your theory. So let's start here at a cardinal point, and this is typically the way they are numbered: points 1, point 2, point 3, and point 4. So for each one of these points, they've got distinctive pressure and temperature, as I pointed out. So what's going on at point number 1? Well, we've got low pressure, superheated vapor at minus 10 degrees Celsius. It's superheated at minus 10 degrees Celsius. Where in my system would that point be? Any ideas? Where do I find low pressure superheated gas?
The evaporators.
Pardon me?
Evaporator.
Right, at the exit of the evaporator. Okay, and so we can say that this point is at the exit of the evaporator, but I'm going to put it a little bit different terms. I'm going to say at inlet to the compressor. And the reason I'm saying inlet to the compressor, because right at that point there, the pressure starts to go up. Okay, so the outlet of the evaporator might be over here, where it's saturated, or like, you know, for my drawing here, I only show 5 degrees of superheat, and then it goes directly into the compressor, but it probably would pick up more superheat than that. I mean, it could be that at the inlet of the compressor would be over here somewhere, but you know, I'm just giving you an example here. So right now, the way that it's drawn is right at the inlet to the compressor. And the compressor now is going to boost that pressure up to high side pressure. So let's take a look at some of the conditions here. High side pressure, we've got 1190 kPa. I don't know, maybe it's 1200. I don't know. I can't read it very well. And let's see what the temperature is. Well, here's a line of constant. Oh, by the way, let's take a look at this compression. We've got lines of constant entropy. So the isentropic compression is going to take us right to there. So if I wanted to draw this very, very accurately, I would show a line that follows those compression, or pardon me, those isentropic compression things. But the program that I used just basically connects the dots. So it gives a straight line. Realistically, it should be a curved line that follows the isentropes, but it doesn't. It's just, this is what the program does. Just draws us a straight line from point A to point B, or point 1 to 2. So there's our adiabatic compression. And now if we take a look at the temperature lines, the lines of constant temperature, we're between this one here, which looks like it's 100 degrees Celsius. That's 100 degrees Celsius. 100. And then the next line over is this one here, 120 degrees Celsius. And it looks like this point is like right smack in the middle. So what this means is that the discharge of the compressor, the temperature of the gas is 110 degrees Celsius. Isn't that crazy? So here's a little bit of Dave's power engineering advice to put in your little power engineering toolbox. Is if you're working in an ammonia plant, one of the characteristics of ammonia is very high discharge temperature. So these pipes are going to be uninsulated. The discharge pipes in the compressor are uninsulated because we're discharging into the condenser. So let's cool it off as much as we can before it gets to the condenser. In other words, what I'm telling you is, don't touch the pipe. Don't touch the pipe. You'll get burned. Okay. And the other thing is, ammonia gets really hot when you compress it. It's one of the thermodynamic characteristics of this particular refrigerant. It's different for different refrigerants, but ammonia is going to be stinking hot. And so this makes it kind of hard on the compressor, on the lube oil, on the valve plate assembly and things like that. And what you're going to find is when we look into a little bit more detail about the compressors, is we'll see things like a high discharge temperature cutoff is fairly common on ammonia compressors. Okay, so if it gets to say, let's say 130 degrees Celsius, the machine will trip off. Okay, so so here we are at point 2, and we are at the inlet of the condenser now. And so we are going to give off the heat. First of all, we're going to give off the heat of compression, and we are going to turn it into saturated gas, and then we're going to continue to give off heat in the condenser, always at a constant temperature, in this case of 30 degrees Celsius, because it's going to be at that 1190 kPa. And then, of course, we're going to subcool a little bit until we get to point 3. At point 3, we've got high pressure, subcooled liquid. And we are going to now put that into the evaporator. And we're going to control its flow using a metering device, a metering valve. Maybe it's an expansion valve. Maybe it's an orifice plate. Maybe it's a capillary tube. Maybe it's a float control, a high side or low side float. So this is where our metering device is. And across the metering device, we've got a delta P. And that delta P drives the liquid refrigerant through and into the evaporator. And what we have to know then is that this is isenthalpic. Okay, isenthalpic. So in other words, the enthalpy at point 3 before it enters the evaporator is the same as the enthalpy of the liquid at point 4. And I can draw a little line down here, and I can say, well, what is that enthalpy? Well, that's 180, that's 360, and I don't know, let's say that that's 250. I'm just guessing right now. What's the unit? Kilojoules per kilogram. So this is specific enthalpy. If I know how many kilograms I'm circulating per unit time, then I know, well, actually, I'll get to that point next. So it's coming in at 250 kilojoules per kilogram, and it's boiling. Now this is the same as like a boiler, right? We've got feed water that enters the boiler, and the feed water that enters the boiler has a particular amount of enthalpy. And when we boil it, and then we got steam that leaves the boiler. In this case, we've got refrigerant gas that is leaving the evaporator, and it looks to me like it's about 1440. We'll use that number, close enough. Kilojoules per kilogram. And so how much heat was absorbed in the evaporator? Well, the heat absorbed in the evaporator is what we call the net refrigerating effect. And the net refrigerating effect is always expressed in terms of per kilogram. So it's kilojoules of heat absorbed in the evaporator per kilogram of refrigerant that's circulated. So net refrigerating effect is H1 minus H, I can say H3, because H3 is equal to H4 because it is isenthalpic. You know, 0.4 is really only useful in terms of telling us what the pressure is, but not what the enthalpy is. So NRE is H1 minus H3. In this case, it is 1440 minus 250, and oh boy, can you believe it? I'm going to pull my calculator because I just don't want to sound stupider than I normally do. So 1190 kilojoules for every kilogram that flows. And so then if we know our mass flow per unit time, so let's say kilograms per second, okay, if I go times kilograms per second, then I'm left with kilojoules per second. So in other words, I could determine my kilowatt rating or tonnage rating of the evaporator. So the evaporator kilowatt rating or evaporator capacity depends upon mass flow. Net refrigerating effect does not look at mass flow, but now that we know the actual mass flow, we can take the NRE times the mass flow, and what we're left with is kilowatt rating, because we're going to get kilojoules per second. And that kilowatt, I'm going to put E there, but this is not kilowatts electric. This is the kilowatts of the evaporator. And I know that there's 3.877 tons of refrigeration per kilowatt. So, you know, what I can do is convert that into tons of refrigeration as well, using that conversion factor that's in your Pan Global academic extract or academic supplement. So anyway, net refrigerating effect is obviously pretty important, because it says that for every kilogram of refrigerant that enters the evaporator, how many kilojoules do we remove, do we transfer? So let's see what would happen if we did not subcool. And so I'm going to use a different color here. If we didn't subcool, let's say that we end up with saturated liquid entering the evaporator. Well, it's got more energy when it enters. As a matter of fact, let's say that this one here is, I don't know, 280 kilojoules per kilogram. And if it's still leaving at 1440, then our NRE is going to be equal to 1440 minus 280, which is going to be 1160 kilojoules per kilogram circulated. And so you can see that subcooling is beneficial. If I subcooled it even more to say 10 degrees Celsius, so let's say I had really cold condenser water. My condenser water was 5 degrees Celsius, and I could cool it down to 10 degrees Celsius. Then you can see my net refrigerating effect would be even greater, because here we would be at, say, I don't know, let's say 200. So we've got 200 kilojoules per kilogram and 1440, then we would have 1240 would be our net refrigerating effect for this example over here. Okay, so subcooling, bottom line, is our friend, because subcooling, we end up with a greater net refrigerating effect. And how do we do that? What we are doing is rejecting more heat in the condenser and reducing the amount of flash gas. So this represents how much gas flashes. And in this case here, it looks like it's about 9% of the gas flashes, which would mean that 91% of the remainder is liquid, and it's going to absorb heat. Whereas in this situation over here, where we had no subcooling at all, we've got, let's say, 17% flash gas. And this flash gas doesn't transfer heat very well. You know, transferring heat to a gaseous substance is never a very effective mode of heat transfer. We can transfer heat much better liquid to liquid, or solid to solid, or solid to liquid, but gases aren't very great transmitters, conductors of heat. So it's just occupying space in the evaporator, number one. Number two is, if I've got a greater NRE, so my NRE is maximum, that means that my mass flow of refrigerant is going to be a minimum for every kilowatt absorbed in the evaporator. Okay, that's not kilowatts electric again, that's kilowatts in the evaporator. Here, I'll put a V there. Here, I'll put AP as well. Kilowatts of the evaporator. Okay, so in other words, we're circulating less mass of refrigerant for a particular heat transfer ability for the evaporator, right? Let's say I want to absorb 10 kilowatts of heat. Well, do I want to circulate 20 kilograms of refrigerant for every 10 kilowatts of heat? Or do I want to circulate 10 kilograms for every 20 kilowatts of heat transfer? And the answer is I want to circulate less refrigerant to get the same refrigerating effect, because that yields benefits over here in the compression. Because if I'm compressing less refrigerant per unit time, then I'm also consuming less power in the compressor. Okay, so that's our NRE. We're going to take a break shortly. Just hang on there. So from this point here, that's the enthalpy that the refrigerant brings into the evaporator, and we can determine what its flash gas here by knowing the lines of constant superheat, or pardon me, the lines of constant quality. And then this is the enthalpy of the refrigerant that's leaving the evaporator. And so then the work done in compression is this amount right here. That's work done per kilogram. And then again, you know, if we know how many kilograms per second are flowing, then we can get the power. And now this is the power output of the compressor. This is not the power input. It doesn't look at the efficiencies. It doesn't look at the motor efficiency or the compressor efficiency. We know that there's friction and all that kind of stuff. But if we know the kilograms per second, and let's say we've had very little flash gas, we've had a very high NRE, so we don't have to circulate a lot of kilograms per second, that's now the power output. Okay, that's the kilowatt output of the compressor. In the same way that we determine the kilowatt output of a pump, right? Same type of idea. So the work done per kilogram circulated is going to be H2 minus H1. And if we know the work done per kilogram, and we know the amount of heat transferred with the evaporator, we can determine the coefficient of performance. And I think that that's about all that I wanted to look at. We can also take a look at what is the rating of the condenser. So if we want to know what the condenser capacity is, again in kilowatts, so we'll go kilowatts C for condenser. That's going to be H2 minus H3. Okay, and if we know the mass in kilograms per second, then we'll get a kilowatts rating. Notice that the condenser must be rated for a greater heat transfer than the evaporator, because all the evaporator is doing is sucking energy out of the refrigerated space, which is a small amount, but the condenser has to discharge. It's going to get rid of the heat absorbed in the evaporator, and it's also got to get rid of the work done by the compressor. Okay, time for a break. That's basically the recap of the theory. You know all of the bits of the equipment and what the system flow is. We go from point 1 to 2 to 3 to 4 to 1 to 2 to 3 to 4. You know, we compress, we condense, we expand to low pressure, we boil, and we do this simultaneously. All of these functions are taking place simultaneously in a refrigeration plant. So the next thing to look at is, okay, so in this particular objective, this is what objective, I guess it's still objective 2. So objective 2, they also talk about compressors. And we know about compressors. We've just studied them in air compression. And we've also studied this last year. So reciprocating compressors that we use in refrigeration service have some special features that just you need to know. First of all, they can be hermetic, they can be semi-hermetic, or they can be open frame. Now, the hermetic design, this is like the scroll compressors we see in the Synovus HVAC chiller. You know, the one you did a competency on it last year for the HVAC. The semi-hermetic, this is the cascade system used, semi-hermetic or serviceable hermetic. So these ones here we can actually dismantle, take apart. We can service the crankshaft. We can do work on the bearings and do piston rings and stuff like that. We can actually disassemble them. Whereas a hermetically sealed one, we can't actually take it apart, right? We can't take it apart and rebuild it and put it back together. So that's the difference between a hermetic and a semi-hermetic. And then there is the open frame, which we don't have one in the Synovus building. But let's talk a little bit about why we in fact have hermetic and semi-hermetic. It's all about shaft sealing. So what we are trying to do is keep the refrigerant in the system. And one of the characteristics of refrigeration compressors, in particular reciprocating machines, like the title says here, is the crankcases get refrigerant in them. They basically draw in refrigerant from the evaporator. The evaporator refrigerant first goes through the crankcase. And so how do we seal the end of the crankshaft when it sticks out of the housing? Well, if the shaft of the crankcase sticks out of the housing, we've got something that's called an open frame machine. So we're going to need fancy mechanical or packing type of seals, right? Mechanical seals or packing glands made of a special type of packing that's compatible with the type of refrigerant that we're trying to keep inside. Whereas if we've got a hermetic design or a semi-hermetic design, the drive motor, the electric motor, is sealed within the refrigerant containing parts, so we don't need sealing. So that's the advantage of the hermetic and semi-hermetic, is we don't need this business anymore. But still, so many machines out there are open frame, whether they're screws or whether they're recip machines or whether they're rotary compressors. These larger industrial types of compressors are typically open frame. And the advantage of that is just simply that we can service the electric motor without dismantling the compressor. Now, we did see a video about, I was asking you folks, what's the big massive spring on top of the valve plate for? And the answer was it was a safety head. So in case we do get liquid inside of the cylinders, I mean, for an air compressor, do we ever get liquid inside? Nah. But for a refrigeration compressor, we could get liquid returning from the evaporator. If we have overfed the evaporator and we've got a low load condition, we could get liquid being carried over. And in case that happens, because the liquid is incompressible, instead what we're going to do is take the valve head, or the valve plate, or the entire head actually, and hold it in place with a massive spring. And the assembly is called a safety head. So that if the cylinder pressure rises too high to prevent the machine housing from actually blowing up, the head or the valve plate, either way, will lift from the cylinder block and it will relieve the liquid. So that's one of the important features that you need to know about a refrigeration compressor, is that they have safety heads. Now we know about unloaders, and so we may have multi-cylinder machines that have got constant speed unloaders, same like we have with the air compressors. Now this one here is a little bit interesting. So we know that some refrigerants are miscible, and if in fact we do have a miscible refrigerant, uh, then what happens is the lube oil becomes diluted. It loses some of its viscosity. It loses some of its lubricating qualities. And on a startup of the machine, the refrigerant is going to boil in the oil and it's going to make foam. And so what we do is typically in the crankcase, we're going to have a heater. And the heater is going to be on all the time. And the whole idea is with the heat to drive off refrigerant that is absorbed in the oil. As for oil requirements, it really depends upon the type of refrigerant. So we will find using basically mineral oils, and those mineral oils are going to have like a low pour point, which is the temperature at which the stuff stops flowing, or a low flock point, which is the point where waxes start to come out of the lube oil, and also low carbon residue, because as we saw with the ammonia compressor, we could easily get 110 degrees Celsius coming out, and we don't want the oil to break down and form carbon. But we also have, for certain types of refrigerants like R134A, we've got other oils, polyolester oils, And so certain refrigerants require synthetic lubricants because they're incompatible with mineral oils. And so you'll hear the term polyolester oil, especially if you've got an R134A machine. There's an example of a machine that doesn't like mineral oil. It wants a polyolester oil. And as for cooling, we know with air compressors, we see air cooling. And with a refrigeration compressor, we're not doing that. It'll be liquid cooled in the case of a large ammonia compressor, or like the one we saw the video of, it'll be refrigerant cooled. So for example, a hermetic or a semi-hermetic machine is sucking in cold refrigerant from the evaporator, circulated around the engine windings, the motor windings, and the crankcase and stuff, so it's cooled by the refrigerant that comes through it. Now, another thing that's mentioned is the liquid receiver, and just so you know, it is an ASME Section 8 vessel, which also means it's going to have a CRN if it's going to be installed in Canada, according to the B51 code. They are designed to high side pressure, and of course that means we're going to have a pressure relief valve on it, and typically what we see are these duplex pressure relief valves. These pressure relief valves are not going to have tri-levers, so you can't test them. And what we will have is basically a three-way valve. It's one of the few places where it's permitted, but the three-way valve will select either one valve or the other one, so we can take the valve off. Because they don't have tri-levers, we actually have to get them tested, recertified, or replaced every 5 years, according to CSA B52. Now, other things we might find, we may in fact find on some of them a gauge glass. And it could be a reflex style gauge glass. Or maybe we've got these bullet style gauge glasses. We might see something like that. And there you go. The liquid receiver is going to accept the liquid from the condenser so that all of the liquid drains from the condenser, and that way we use the entire surface area of the condenser for heat transfer. And of course, there's also the storage business here. The size of them, the capacity is such so that what we can do is pump the refrigerant from one part of the system, or pump out the system and store the refrigerant on site inside this thing, isolate it, and so that way we can expand the plant. And this is going on all the time. The plant gets a little bit bigger, they add another cooler or this or that, and so they have to add extra piping, they add another condenser, they add this, they add that. Always going on in the land of refrigeration. So we can pump the refrigerant into this thing without it being more than 80% full, according to CSA B52. Now, the other thing that's mentioned in your Pan Global in this particular chapter is the manual expansion valve. And a lot of times people think, we don't see those anymore. It's all electronic. It's all automatic. It's thermostatic. It's this, it's that. Where would you see a manual one? Well, first of all, what does the expansion valve do? It's a meter device, one of the types. And the manual is the simplest type, of course. It's got a handle on it, and you set it, and based upon something, right? And so if this is going to the evaporator, what we'll do is probably look at a pressure gauge. And I put a pigtail. It doesn't need a pigtail. It's refrigeration. And so we're going to look at a pressure gauge, and we're going to see, is it at the set point? And then we'll probably adjust it a little bit this way or a little bit that way. And sometimes this is like a vernier valve where we'll have markings, gradations on it, so we know how far it is open or closed or something like that. And so you think, well, when are we going to do this? When are we going to operate one of those things? Well, where we find them is, let's say I got a very large complex system with many evaporators and stuff like that, and I want to be able to balance the refrigerant flow so that all of the evaporators are getting the liquid that they need. And so they could be balancing valves where we kind of set them and forget them when the system is initially balanced. But let's say I've got a low side float. And we'll take a look at one later, but it's a float type of metering device that's trying to maintain a constant evaporator liquid level. And being a float, sometimes they screw up. So we can have isolation valves before and after the low side float on the float cage, and then we'll need to have some sort of a manual bypass valve. So we can use this as a manual bypass. And finally, the liquid overfeed evaporator, which we're going to look into a little bit later in more detail. But the liquid overfeed evaporator doesn't care so much because we overfeed it with refrigerant anyway. And typically, 3 times the amount needed is fed to the evaporator. So that means we're putting lots of liquid, and we're getting lots of two-phase liquid and gas come out of the evaporator. So these particular units aren't too fussy about how much liquid is fed. So if we use a manual expansion valve, it's not such a big deal. We're not going to damage the compressor. So they are still in use, and it's important that you know what they're used for. Now, as for evaporators, there are lots of ways that we can categorize them. So I've got basically method A, method B, and method C, different ways we can categorize evaporators. So there's the dry, which in fact isn't dry, okay? It does have liquid in it for sure, but the amount of liquid varies with the load, and a certain portion of the heat transfer surface then is not going to be exposed to liquid. The flooded evaporator does a little bit of a better job because it maintains the heat transfer surfaces with boiling liquid all the time. And we do know that the heat transfer to gas is lousy, but the heat transfer to liquid, especially the latent heat of evaporation of the liquid, is really, really good. And so a flooded evaporator is far more effective. You get a greater heat transfer with the flooded per unit time, per unit size, than for the dry type of evaporator. Now, number 3 is the liquid overfeed evaporator, which is the most important in industry today. This is the royal emperor of evaporators. Now, it is covered briefly in your fourth. Okay, they got a picture in there, and they talk a little bit about what the liquid overfeed evaporator is. It's ignored in the third, which is just a terrible oversight. And hopefully with the new edition of the third class, they will address the liquid overfeed. But I am going to cover it, okay? I am going to cover the liquid overfeed because it is so important. If you find yourselves working in a refrigeration plant, you'll be very confused. You won't know what to make of this thing unless we actually talk about it. Now, then other categories. We can say that it's a frosting evaporator. And so then this one here is going to be operating at less than 0 degrees Celsius. And because of that, it's going to build up frost. And the frost will impede the flow of air. For example, if that's our refrigerated medium, it'll impede the flow of air. So, we have to have some sort of a defrosting mechanism, and we're going to have wide fins for the heat transfer surface. Whereas if it's a non-frosting, that would be for sort of like HVAC systems that are greater than 0 degrees Celsius. And so here we would have a coil where the fins are going to be much closer spaced to maximize the heat transfer ability of that particular type. And we don't have to worry about defrosting it. And so where we saw these is we had the frosting type was the CO2 evaporator in the Cascade, and the non-frosting type was for the glycol cooler. Of course, with the glycol, that wasn't actually an evaporator. We were just circulating secondary refrigerant. But if, in fact, we did have refrigerant in there, that would be an example of the fin spacing for a non-frosting versus a frosting type of evaporator. Now, as for types of construction, this is all like rehashed from fourth. We've got bare tubes, we've got fin tubes, we've got plate surfaces, and we've got shell and tube. And I think you know all about that stuff, so you can read that over on your own. Now, here is the liquid overfeed. And the first time I saw one of these things, I was already an inspector. And just so you know, the inspectors in Manitoba don't just inspect boilers. We inspect pressure vessels, pressure piping systems. We did gas and oil inspections. And a big chunk of what we did was refrigeration plant inspections. And I went to a small bakery, actually a fairly large bakery, I guess, in north end of Winnipeg, and called City Bread. And this is the first time I saw a liquid overfeed system. It was a 50 tons of refrigeration machine. And when I walked in there, I was astounded because everything you see on this slide here, I saw there, and I didn't know what was going on. Okay, so let's take a look at what's going on. The key to the liquid overfeed system is this thing here, which is the low pressure receiver. Now, sometimes it's called an accumulator. Okay, so for example, on the diagram on the right, they're calling it an accumulator. This, by the way, is from a guy named Roy Dosat, and the book is called Principles of Refrigeration. And I would highly recommend that you get this. In particular, get the SI edition. And this will take you all the way to clas. It's such a fantastic book. It's really, really good, especially if you're into refrigeration. Anyway, let's take a look at what we've got here. We've got a float control. And so this here is our metering device. And this is called a low side float. And low side, we know, is the low pressure side. So let's just sort of divide this thing up. What we have here is the high side, and on the other side we've got the low side. And we've got a float that is sensing the level inside this low pressure receiver. Now, it's sort of like a low water cutoff, and this particular one has got an electrical contact that operates a solenoid valve, and so the solenoid valve is basically our metering device. It's going to be on or off. And what it's going to do is let in refrigerant to maintain a particular level set point. So this is liquid R717 ammonia. Now we've got a pump, it's an ammonia pump, and we're going to draw the liquid and we're going to circulate it through the evaporators. And maybe we might have manual balancing valves so that each one is getting the proper amount of refrigerant. But they're going to be fed 3 times plus the amount that they can actually evaporate. So in other words, they're going to be really, really wet, okay? They're like flooded evaporators, sort of, kind of, but it's with positive circulation of ammonia through the evaporator coils. And so then what we get here is two-phase mixture coming out, both gas and liquid, and the liquid falls down, and the gas goes, well, look, there's like a dry pipe type of thing here. And so that the compressor is only going to draw low pressure gas. And the moisture will get dropped out back in. And so we're going to keep recirculating it. But of course, the compressor is always drawing away gas. And so we're always going to need a little bit of makeup, right? So the solenoid is going to open and shut and make up to this low pressure receiver. And then we condense the gas, and then it gets stored in the high pressure receiver. But this here is kind of the interesting bits about this liquid overfeed system. So when you look at this thing, I want you to think of it as being like a boiler. So what have we got here? A steam drum. And here we've got our heat source. So we've got a room that's hot, right? So this is like our furnace. And so what we have here are risers. And we've got internal recirculation. And we've got a steam separator device in there, cyclone separator, chevron, right? And then what we have is, this is a controlled circulation type of boiler. So it's got some forced circulation. So really, it's very much like a boiler. And of course, we need to have feed water. So we've got a single element feed refrigerant control. And we've got an on-off two-position single element feed water or feed refrigerant solenoid. Okay, it's like a boiler. And if you take a look, this is another one from DOSAT. And here you can see where we've got a manual expansion valve that can be used to bypass the float control, just in case the float control isn't working. So normally the refrigerant goes in here through a mechanical feeder and up that way. But if this thing's buggered up and we've got to take it out of service, then we can isolate it and feed the refrigerant in through the manual expansion valve. Anyway, there you go. This is a ammonia pump over there. It's pretty neat stuff, and it's very important. Even like a bakery in North End, Winnipeg has a liquid overfeed evaporator. So, okay, so the next is direct and indirect refrigeration. And so if we take a look at the cascade system, we had 2 systems there. And yes, there was a cascade, but we also had a CO2 where the evaporator was directly communicating with the refrigerated space. So here we had a refrigerated room, and we had an evaporator in there, and that evaporator had CO2 in it. So if this evaporator should spring a leak, you don't want to be in the room because you will be asphyxiated, because the CO2 is going to displace the air in the room, and you're going to suffocate, right? So this is called a direct system, where the heat transfer equipment is directly incommunicated with the refrigerated medium. And the refrigerated medium doesn't have to be air. You know, maybe we're cooling off the air, but maybe we're cooling off a liquid. Maybe we're cooling off milk, you know, that's been pasteurized, so it's been flash heated, and now it needs to be flash cooled. And so we'll have the evaporator coil stuck directly in the milk. So that's an example of a direct refrigeration system, whereas indirect would be the other system we had that used glycol. As a matter of fact, we had a little circulating pump, and it was propylene glycol that was in that system, and we circulated that through the refrigerated space. So here's our glycol in here, but there's no chance that the gaseous refrigerant could escape into the room. If this thing springs a leak, you're just going to get, you know, droplets of glycol, and you're going to get a puddle on the floor. But you're not going to get, hopefully, no refrigerant will get into that room and cause us problems. So that's the basic difference between a direct and an indirect system. Now, direct systems are also called DX systems. So you're going to come across that term, and I might use it too. A DX means direct expansion. Now, the indirect systems, the stuff that we circulate by pump is called a secondary refrigerant, and you need to know that term. Okay, you need to know what a secondary refrigerant is. And in the system that we ran with the Cascade, it was propylene glycol, but it could be water. So we see water being used for HVAC. Water would be the secondary refrigerant that we circulate with chilled water pumps. And if we've got, say, a skating rink, or maybe we've got a cold storage facility that is circulating brine, it would be something like calcium chloride brine, which is really good. It gives us a freezing temperature down to minus 51 degrees Celsius. So this brine here is commonly used, say, for skating rinks, cold storage, that sort of thing. So here's the indirect system. This is out of your Pan Global. It's actually Pan Global stole this from DOSAT as well. But here you can see this is the refrigerant circuit here. This is our compression refrigeration. But what we're doing here is cooling off brine. So we've got a little pump, and the brine then is going to the refrigerated space rather than the refrigerant. Now, if it's an HVAC service, like I said, chilled water, usually it's 4 degrees Celsius. That's pretty standard temperature. Ice rinks will use a calcium chloride brine, but other brines that are in use would be some sort of alcohol, glycerin, ethylene glycol. Less so now with the ethylene glycol because it's toxic. And what we had at our lab, our secondary refrigerant, or our brine, was propylene glycol. And the whole idea is so we can achieve low temperature without the stuff freezing. So here is an HVAC chiller. And this particular HVAC chiller uses a centrifugal compressor. And boy, I don't know how much I want to say about this, because this is like first year lab type of thing. And I don't think that this is in your fourth, but let's just take a look at it very briefly. What we have here is an evaporator, and we've got a condenser, and they're pressure vessels, and they're designed to ASME 8. And so what we have is liquid in the condenser, because what we've got is condenser water. So we've got the CW pumps, or pumping CW in and CW out. And it's cooler than the temperature of the refrigerant. So the refrigerant condenses and forms liquid, and the liquid goes through this pipe and builds up down here into a float. So there's the evaporator float. This is our metering device, and so what happens is when the liquid rises to a certain point, it'll open up and allow refrigerant in. And the whole idea is we're trying to maintain a fairly constant refrigerant level boiling away in the evaporator. And then what we're going to do is put a whole bunch of tubes in there that carry the chilled water, in other words, the brine. So our chilled water goes in, it's pumped in, and the chilled water goes out at 4 degrees Celsius and goes around the campus, if you will. Now, the boiling action is quite vigorous, and we are going to get droplets going in. So we're going to have chevron dryers here. And it's called an eliminator, but we basically got these chevrons here, just like we see in a steam drum. And now we got dry, low pressure, cold vapor gets sucked into the compressor and discharged into the condenser. And there you go. There's the whole thing. Now, with these chillers, okay, well, this one here looks to me like it's a screw. I can't remember where I got that picture from. Maybe that's from York. Now, the evaporator, it's interesting. The evaporator here is all insulated. And anything that's under low pressure is insulated with this black insulation. You've seen this. Now, this here is the condenser, and you can always find a condenser because it's uninsulated, right? The whole idea is to give off heat. Now, from this compressor, we've got a discharge line that discharges the gas into the condenser. We've got CW in and out connections. And somewhere there will be chilled water connections. They don't show up on that picture. As for the compressors, what do we see? Typically a two-stage centrifugal machine. Very, very common. But as you noticed in the HVAC chiller on the 4th floor of Synovus, we had multiple scroll compressors. There are 4 scrolls that were sequenced for capacity control on that particular machine. So scrolls and centrifugal machines are the most common. This one here surprises me a little bit because it appears to have a screw, or maybe it's a rotary compressor. I'm not too sure, but it certainly looks like a screw to me. Now, here's something that's new in the 3rd for sure, and this is the economizer. Now, this is not the kind of economizer you saw on the Cascade system. It's not the kind of economizer that you studied in 4th class for a typical compression refrigeration system. This is an economizer that specifically, this term is applied to chillers. Now, what does it do? It makes operation more economical, okay? So that's why we have an economizer. Increases the efficiency. And what we're going to do is take the refrigerant and flash it at an intermediate pressure. And what's it going to do? It's going to cool the motor, which is a good thing. We want the motor to be cool. And so this particular thing, this is the motor armature or the rotor. And it's going to be surrounded by stator windings. And this is going to be a semi-hermetic machine, because most of these are in fact semi-hermetic. There are some that are open frame, but most of them are semi-hermetic. Now, the next thing is they are going to increase the net refrigerating effect, which is a really good thing, because we know that when the net refrigerating effect increases, then the mass flow of refrigerant decreases for every kilowatt of of heat transfer in the evaporator. And if our mass flow decreases, then that reduces the work done in compression for every kilowatt of energy absorbed in the evaporator. Okay, so that's what's going on with the economizer. And there's one other thing that we should look at here is, and I'm going to add this, isothermal compression. Now, we're not going to achieve isothermal compression, but we know that adiabatic uses a lot of energy, in particular because we retain the work of compression. We retain it with the compressed gas. And if we're retaining it and not sending it outside of the system boundaries, then we get a more rapid or a steeper increase in the gas pressure, which means that we do more work in compression. We wouldn't like that. We would like things to be isothermal. We would like to remove the work done by compression. The heat of compression. We want to remove that and follow an isothermal line, which is far more efficient. And what we're going to see is that this economizer is also going to have an intercooling effect, because that's what we did with air compressors, right? Now, the only way we can intercool is we need to have multi-stages. Okay, you can't intercool a single stage machine. What we need to do, if we're going to intercool, we need to have 2 steps of compression, and in between we are going to do some intercooling. Well, what you know about intercoolers is this. I got a reciprocating machine here with a low pressure cylinder on the left and a high pressure cylinder on the right. And then what we're going to do is take the gas and we're going to put it through an air-cooled or water-cooled cooler, and we're going to put it into the HP cylinder. Well, the refrigeration is really, really neat because we don't need cooling air, we don't need cooling water. What we can do with refrigeration is we can directly inject the refrigerant into the gas. Okay, so this would be like a non-contact intercooler, but we are going to be using what's basically a direct contact intercooler, which is extremely important. The Pan Global says it's not done anymore, and that is entirely wrong. It is the most important method of intercooling, and really what this is, if I want to give this boiler terminology, we're going to call that a desuperheater, because that's really what's going on. So let's take a look at where this economizer fits. This is it right here, the economizer. And here we've got our low pressure evaporator. Here we've got our high pressure condenser, and the economizer has a pipe that goes in between the 2 stages of compression. There's compression stage 1 and compression stage 2. So that means that this is at intermediate pressure. So LP is also low temperature, HP is high temperature, so IP is also at intermediate temperature. Now, when we take a look at our pressure enthalpy diagram, and I draw my curve looking something like that, and let's say I got some subcooled liquid, and the subcooled liquid is going to enter into our evaporator, and we're going to have a certain amount of flashing going on. And then the liquid is going to absorb heat as it boils, and then it's going to get superheated, and then what I can do is compress it adiabatically to some high pressure and high temperature, and I have lousy volumetric efficiency and all that kind of good stuff. And we've got this type of situation going on here. But what I can do is break this down into two stages of compression. I'm going to compress it adiabatically to an intermediate pressure, and then I'm going to put cool intermediate pressure refrigerant in between the stages. Okay, where did I get that refrigerant from? I put it in to the evaporator and a certain amount flashed. The amount that flashed, the kilograms that flashed, are going to absorb heat basically by going through the motor and then into that in-between stage, and it's going to cool off the refrigerant in between the stages of compression. The remaining amount of liquid in the economizer is now saturated back to the saturation line, and it's going to boil in the evaporator. Now the second stage of compression is also going to compress adiabatically, and you can see we're at a much lower temperature of discharge than we were with just a single stage of compression. Okay, so let's take a look at this again. As a fully intercooled type of machine with an economizer. I'm going to start here. The liquid enters the evaporator. A small portion of it flashes into gas. When it flashes into gas, it becomes saturated liquid and flash gas. The saturated liquid goes into the low side pressure, but the flashed gas at intermediate pressure enters, mixes here with the discharge from the first stage of compression and has an intercooling effect. The liquid then goes from intermediate pressure to low pressure. We do still get flash, but much less flash gas. And if we have less flash gas, we get a greater net refrigerating effect. And that means that we circulate less refrigerant per unit time. And it's a win-win-win-win-win situation. And I got a slide here. This one shows it really well. So this is just a two-stage compression system with intercooling. And it's exactly what I tried to show you with that tiny little diagram, but now with more clarity. So you can see without intercooling, it's this sort of light colored blue. And we see that this, really, this is the adiabatic compression. And this is the same as before, where we got 110 degrees Celsius discharge temperature. But with the intercooling, with the first stage of compression, I'm up to, say, 45 degrees Celsius. That's my discharge temperature. And the flash gas cools it back down until it's saturated. I compress it again in the second stage. And here, my discharge temperature looks like it's about 60 degrees Celsius. So much cooler operation, better volumetric efficiency, and greater NRE because although I've got flash gas at an intermediate stage, I use the flash gas here for intercooling, and the remaining liquid enters into the evaporator, much less flash gas, let's say 8% flash gas, and so a much higher NRE than without intercooling. Difference being that much extra heat is absorbed per kilogram being circulated.